Hello again and welcome. A few of you have asked for more details about this old Arb. First of all, I designed this Arb roughly 35 years ago, so this is certainly not new technology. I had mentioned that it's not only just an Arb, it's actually a recording device. So again, I have a input jack as well as an output jack and a trigger in and a trigger out. So you can set this thing up to record the waveform, it'll store it into RAM, and then you can play back on this channel here. So I had shown this with a sine wave. Of course you can do other waveforms with this. Here for example, you can see we have a triangle wave, and I had mentioned that you could change the delay. So here I've got the oscilloscope triggering off of channel 2. And here's our trigger pulse. The scope's just warming up, so give it a second. So that is the trigger out. And I mentioned that I could do a delayed trigger. So if you watch this waveform, I'm just going to add some delay. So again, what I was using this for is I would attach this to an old analog oscilloscope. Again, I didn't have a digital scope back then. And this basically made my analog scope act somewhat like a modern digital scope. So I'd mentioned that this has two ports on the side of it. One of them is an RS-232 port. So the way this worked is this would be attached to my desktop PC, and I had written some software that would control the Arb. So we could download the waveforms that we capture, and I could upload my own custom waveforms to the Arb. It may be possible to set that up again under a DOS box or something and get that working. I'm not going to do that for this demonstration, but that's basically how the Arb worked. So to get started, what I'd like to do is show you what the inside of this box looks like. So the first thing we're going to do is clear off our desk a little bit. Should mention that this oscilloscope that you're seeing me use here, this is a part scope that I bought to try and repair my normal scope here in the background. That thing went on the fritz, and so I bought this other one for parts. You can see I don't have the case for it. The data acquisition system on it is out of my original scope. That's what I bought this for. LaCroix had actually changed out the acquisition system on this scope. Alright, let me get this thing out of the way. I'll show you around the box. First of all, this is the AC power fuse box here. This is your main power on-off switch. See on the back, there's a integrated heat sink. On the other side, again, we have the two connectors. Again, the RS-232 and the Centronics port for the printer. Looking at the front, I don't remember what I salvaged this keypad off of. It could have been like a remote control possibly, or possibly a calculator. I know it's been too long ago. I'm not even sure who made the box for this. Again, this has been 30 some years ago. Don't be surprised by the craftsmanship here. Again, this is a homemade project, so younger me was not as skilled as the older me at construction. Oh, yeah, it's starting to fall apart now. Alright, let's just see here. So here's the lid. Oh. So this is what the main controller board looks like. So down here we have the microprocessor. This would be the main program. This is the RAM for the main processor. These are different PIOs. This is just your basic decoder logic. These ROMs store the default waveforms. This RAM up here is used to store the actual Arb type waveform. I believe that this is our A to D here. You can see there's some bucks. This is a analog devices part. I believe this here is our DAC. Again, we'll go over some of the design. So let's see if we can get this out of here without destroying it. What a mess. You can just see all the resistors and the capacitors soldered across that wire wrap. You can imagine that the signal fidelity for this is not all that great. Let's look at this, all this analog bus bar down here again. I think what I was trying to do is isolate all this analog section from the digital. That's just crazy. Again though, about 35 years old. This is the way I was constructing things back then. I'm actually a little surprised that when I turned this thing on the other day, it just fired right up. Again, this thing doesn't get used, and with it being so old, you'll notice that the wire wrap on this was all done by hand. So this is prior to me purchasing a slit wrap gun. Yeah, all hand wired. Look at all these bypass caps, and then we have some bulks every now and then. Just crazy. So down inside the box, actually made circuit boards for this, which would have been quite rare at that time. Down here, this is the power supply. These are obviously our big filter caps for the plus and minus. Looks like most of these are Nichicon. These two large ones are made by Sprague. But yeah, all the green ones are all Nichicon. Down here you can see the bridge rectifier. Again, that's all made out of discrete diodes. And then, of course, we have a regular transformer for this to try to reduce the noise, so none of that switch mode power supply stuff. This is the DC coupled amplifier. Looks like I made a circuit board for this as well. This piece of coax here is going back to the main control board. So this is the AC signal coming in. Notice up here, these are the two transistors for the push-pull output stage. The fuse is in series with the output. I want to say this was probably a 1 amp fuse, but I think the transformer is actually capable of putting out a few amps. Of course, the pass transistors can easily handle more than an amp. My guess is this piece over here is a linear regulator. Let's just have a look. So this just slides off to the side. Oh, it's not. So here, our pass transistors are a 2N3055. And then this is a 2N3791. That is probably the power pass transistor for the linear regulator. Alright, got the ARB back together. So let's go over some of the documentation for this. Again, I can't stress this enough that this is a home project, so keep that in mind as we kind of go over the documentation for this. So here we're looking at the overview of the hardware. These are the basic building blocks that make up the ARB. We have an analog digital converter, D to A, of course, power amplifier, programmable attenuators, input amplifier, input trigger circuit, output trigger, buffer, computer I/O ports, keypad, liquid crystal display, RS-232, and a Centronics printer port. For you A to D people, the analog digital converter utilizes a 12-bit successive approximation register with a maximum nonlinearity of plus minus a half LSB, absolute accuracy of 2 LSBs. The maximum conversion rate is 50 microseconds or 20 kilohertz, so not a very high bandwidth. The DAC is also a 12-bit converter, has a 350 nanosecond settling time within plus or minus, looks like a half LSB. Let's see, the power amplifier is a quasi-complementary push-pull type, DC coupled. This allows the system to be used for a low current power supply or add a DC offset to their waveforms. The amplifier can sink and source up to 3 amps of current, however it is fused internally at 1 amp. The amplifier has an output impedance of 0.5 ohms, see Appendix A for THD, and frequency response for the amplifier. See, it contains 2 programmable attenuators which are used to select the input and output gains. Attenuators are actually made from 2 separate DACs. Each converter is 8 bits, giving a possible resolution of 256 steps. Each DAC can be selected independently from the keypad by selecting the input or output gain. Here we have the input amplifier. The input signal is first fed into a JFET switch through a 1 meg source resistance with a 100K pull down. Yeah, I'm not sure why I chose to make it work like that. You'd have to ask younger me. Let's see, the input amplifier is made using one of Texas Instruments' Lin CMOS devices. The amplifier chosen has a slew rate of 4.5 volts per microsecond, so not fast by any means. Looks like I'm referring to the buffer as the memory where I store the waveform. The buffer is made up of 12 16K by 1-bit high-speed static RAMs. The buffer's address can be selected by one or two possible ways. The first is an automatic increment mode, which the system hardware will increment the address automatically at a programmed rate. This mode is used when capturing a waveform or during playback. Second method is a manual mode, in which the MPU has direct control of the RAM address counters. In this mode, the MPU can reset the address to 0 and increment through the memory at its own pace. This mode is used for uploading, downloading, and plotting waveforms. So here we're talking about the computer that's used. This is basically the gist of that whole wire wrap board. The computer is based on the Motorola MC6803 microcontroller. So it's kind of like a 6801, but it's using the extended multiplex mode. The basic computer uses up to 32K of ROM, 4K of RAM, 46821, those are the PIOs, are used for the I.O., along with the microcontroller's own I.O. ports. The MC6803 uses a clock rate of 4.9152 megahertz to allow the use of the onboard serial port at 9600 baud. So a modern CPU runs at what? Yeah, so 5 megahertz basically is what this thing is running at. Times have changed. We have the RS-232 serial interface. You can see it's using a CTS and DTR handshake pins, along with the TX and RX. The Centronics port is pretty standard. You can see we just have the data pins, the strobe, the busy, and the ground. And it's interesting. So input coupling. The input signal may be coupled to the first stage amplifier directly or through a capacitor. The two modes are referred to as DC and AC coupling, respectively. Here we have selecting the buffer size. The RAM buffer, this is where we're storing the waveform, can be selected by the user depending on their needs. The system is powered up with the buffer set to 16K by 12 bits. Other settings include 8, 4, and 2K. So this is referring to that delayed trigger resolution. It is used to select the incremental count for the rotary encoder, which will in turn select how much the delayed trigger is affected. This option is useful when the user wishes to view waveforms on the oscilloscope. There are 3 possible settings: low, medium, and high. So no idea of actually changing that resolution based on how fast you spin the knob. Let's see, plotting a waveform. To plot a waveform, once it's been entered into the buffer, press the plot key. See, we could upload a waveform, download a waveform, program module, terminal mode, I have no idea, ROM development tools, convert scanned image, create a standard waveform, and quit to DOS. Yeah, so it's a DOS-based program. And it's pretty funny. So because the screen, this is talking about the PC screen, has a resolution of 640 by 480, so standard VGA, and the buffer can contain up to 12 bits by 16K, the COM program will perform a curve fit on the data to smooth it out. The user has an option to use the spline or interpolation methods for curve fitting. The user may also select no curve fitting by entering a 0. The following is a template used for creating a hand-drawn waveform. You know, before page scanners and everything, they made these hand scanners fit in the palm of your hand. And I think that they selected that format is because a lot of the old trade magazines, like Dr. Dobbs, for example, you could actually drag that thing down the paper, and it had some limited OCR, but then you could scan those software programs into your PC with that. So I supported one of those hand scanners with this. This screen here, this is showing you where you could actually draw your waveform, pass that hand scanner over this, and it would upload that waveform into the ARB. So standard waveforms, we could do pulse, ramp, sine, and triangle. Hints on using Quattro Pro. Quattro Pro and many other spreadsheet programs may be used to alter the graph in the data once it's been captured and downloaded. That's crazy how much things have changed. So this is the SPICE model for the output power amplifier. You can see VCC is set to 30 volts, VEE minus 30. Here's the value of all the components. Here's the diodes. Here's the big pass transistors. How many of you have had to code your SPICE this way? Huh. Oh, here's the money shot. So let's see. Here we're looking at the total harmonic distortion. So 0.275 or so percent. And here's the frequency response. My guess is this was done in PSpice, but you can see it's rolling off here at 1 megahertz. Good enough. Again, we were looking at, what did we say, a 30 kilohertz A to D or something. This is looking at the keypad layout. So this is the firmware that resides inside of the ARB. You can see this is all written in assembler. What a nightmare. A lot of pages of this. Looks like here's some software I wrote, probably in C, for the PC to create the ROM waveforms. Here's a page out of an old book for the 6800. Some subroutine that I probably leveraged in the design. BCD conversions. Various component data sheets. Let's see, where's the analog stuff? Oh, here's the D to A converter. 12-bit DAC from Maxim. Looks like a 8565A probably. Looks like here's the A to D converter. This is a Analog Devices AD5200 or 5210. Yeah, I want to say that back then this part cost like $100. Seems like it was quite expensive. Here's an interesting page. So here's an actual hand-drawn waveform. Here I have a Hewlett-Packard 54111D oscilloscope. I'm not even sure what that is, but I think I've used that oscilloscope then to capture the waveform off of the ARB. You can see those two are basically the same, and you can see how it's kind of repeating. Oh, here you go. So these are waveforms that were digitized and then printed right off of the box. As you can see, the graphics is pretty poor, but that's my first digital printout for home. Pretty crazy. Again, that's all written in firmware and assembler to do this. So here's the schematics for the unit. You can get an idea how old this is. Just look at how yellow the paper is. This is the stuff sheet for that wire wrap board. This is the keypad interface. So here's our matrices of switches. And here's the LEDs. Wire wrap side connector. So this is the connector that interfaces with that keypad. Here we have our A to D converter. Looks like a couple of buffers. Up here we have a DAC, and it looks like that's setting the trigger level maybe for the input trigger. Here's the RAM interface. I believe that this is most of the logic on that main board. Back when schematics were manly. What a mess. Nowadays we'd put all this into one FPGA. It'd run a couple hundred times faster. Higher resolution A to D. Crazy. But again, back then, this is what I had to work with. Here we have the D to A converter. Looks like some trim pots to set the thing up. Again, not a whole lot to this design. So here's the one that everybody wants to see. I don't know why, but this is the power amplifier. It's not a whole lot to this. Again, it's just a basic transistor amplifier. But here you go. So it looks like I have some kind of a buffer amplifier here. Looks like just a 33074, so nothing special. We have our 2 transistor mirror. Again, this is nothing more than a 3055. Looks like it's being driven off of a 5192. On the negative side, we're using a 2N5195. And then that again is driving a 3055. So it's kind of interesting. You can see we're using a PNP to drive the base of this NPN for the pull down. So I'm not using complementary transistors on the output of this. They're both NPN. Here you can see I have some kind of a RC network to tune the output. This is probably there for stability. Here's the 1 amp fuse, and of course here's the output signal. So not a whole lot to this. Here we have the CPU board. So here's the actual microprocessor. Here's the crystal for it. Let's see, we have just a real simple reset. It doesn't even look like we have a watchdog on here. Yeah, just an RC network. That's it. There's the 2 transceivers for the RS-232. Just some simple decode logic is it. Here's the 2 ROMs. Here's the RAMs. And the PIO interfaces. You get an idea here. These schematics basically take up my entire desk. Here's my scope. And here's our transient generator. So yeah, very large. Well, I don't know what else to show you on this. If you have any specific questions, feel free to ask. But I think that's going to be it for this video. Hope you enjoyed the little history lesson. So hopefully, we'll catch you in the next video. We'll see you then. Later. So just a little side story. When I was looking at the documentation for the ARB, I had mentioned that I had used a 54111D oscilloscope from HP. Here we have a HP catalog from 1990. I thought I'd look that scope up because I don't remember ever using that scope. So this is it right here. Features a 2 gigasample per second digitizing rate, 500 megahertz bandwidth. As soon as I saw this, I definitely remember using this oscilloscope. So we didn't actually own the scope where I worked. I rented this for another project. 500 megahertz back then. That was a pretty big deal. I think the fastest scope we had at work at the time was maybe 100 megahertz. At the time, I had just gotten married to my wife, and so we're living in our first house together, and I had this oscilloscope delivered directly to my home. You see, this is what I'm using to collect the data.
Okay.
It's a Hewlett-Packard 54111D oscilloscope.
Okay.
And I thought, we don't have a work place where we had that scope. I don't remember that scope.
Is that the big, really expensive one that came that made me like go, oh my God, no!
Yep, that's that one.
Okay.
Yep. So I looked it up and I was like, oh, I remember that scope.
It was delivered to the house.
Delivered to the house, that's right. Remember how much it cost?
More than the house. Wasn't it like $80,000 or something? Oh.
See, I thought it was way more than that too.
Yeah.
But yeah, basically 27,000.
Yeah, I thought it was worth more than the house.
Yeah. No.
Oh.
Yeah.
Yeah, I really did. I thought it was like $80,000.
Yeah. Don't you it's like you recalibrate all those years, but that's 35 years ago.
Yeah. Yeah. I actually always thought it, in my brain, I thought it was worth more than the house when it was delivered, and that's why we were both so nervous.
I don't remember being nervous about it. I remember you being very nervous about it.
Yeah. Maybe it was that it was more than my car.
That is definitely to be the case.
Yeah, because it was more than 10,000 more than the car. Yeah.
So now if I brought a home scope like that today, what would you say? So you've been married to me long enough that it's like,
yeah. You're not going to ruin it.
I'm not going to ruin it.
The dog's not going to jump on.
Well, there you go.